Hi everyone, I'm Aryan. I'm going to tell you about pseudo-deterministic algorithms for minimum cut problems. This is joint work with Nitin Verma. So let me start by defining a minimum cut. So let G be a weighted undirected graph with edge weights W which are polynomially bounded. A cut set is any set S which is not empty and it's not the entire vertex set. The cut formed by the cut set is equal to the set of edges such that exactly one endpoint of the edge lies within the cut set. So in the picture above, the blue shaded area is the cut set and the turquoise edges are the cut. The weight of the cut is the sum of edge weights. Finally, in some parts of the talk, I'll be talking about ST cuts. So if S and T are two vertices in V, then an ST cut is a cut formed by a cut set S such that S is in the cut set and T is not. So it's any cut which separates S from T. Good. Now let me define the problems. So the minimum ST cut problem is defined as follows. You're given as input a graph, a weighted undirected graph along with S and T. And as output, you need to produce a cut set S such that the cut is a minimum weight ST cut. In the global minimum cut problem, you're given as input a weighted undirected graph, but no S and T this time. And you just need to compute a cut set S such that cut S is a minimum weight cut. Right? Good. Now let me define pseudodeterminism. So let P be a search problem. The domain of P is the set of strings and the range of P is the set of strings. Okay? So for example, you can think of the input as a graph and the range of the function as then, for example, the set of minimum cuts in that graph. Okay? Now a deterministic algorithm A solves P if for all inputs X, A of X lies in P of X. A randomized algorithm A solves P if for all inputs X with high probability A of X lies in P of X. Finally, a pseudo-deterministic algorithm solves P if for all inputs X there exists some Y in P of X such that with high probability A of X is equal to Y. Okay? Note the subtle difference between randomized and pseudo-deterministic. The intuition is that a pseudo-deterministic algorithm is a randomized algorithm with low entropy. That is, for each input, there is a canonical solution which the algorithm will output with very high probability. And an example is the ST minimum cut problem. A graph could have exponentially many minimum cut sets. The output of a randomized algorithm could be a uniform distribution over the cuts, whereas a pseudo-deterministic algorithm has to output one particular cut with very high probability. Now, why is pseudo-determinism important? Well, there are three reasons why I find it important. So the first is a complexity theoretic motivation. Now, pseudo-determinism essentially captures the power given to search algorithms by randomized decision algorithms, right? And if you're not familiar with the term, a decision problem is essentially a search problem where the output set is either 0 or 1. Okay? Now let's say that every decision problem solvable in randomized polynomial time can be solved in deterministic polynomial time. That is, let's say that BPP is equal to P. Does this imply anything for search problems? That is, can every search problem solvable in randomized polynomial time be solved in deterministic polynomial time? That's unclear. What is known is that if BPP were equal to P, then the search problem solvable in deterministic polynomial time would be exactly those problems which have a pseudo-deterministic polynomial time algorithm, right? Good. Now, the second motivation for me comes from low space computation. Now, non-pseudo-deterministic algorithms are hard to use as oracles or as subroutines in low space computation, right? And why is that? Well, let's stay with minimum cut for now. So low space algorithms cannot write down an entire cut on their work tape, right? Because you would need n bits for that. And this is true for many problems, right? So for example, matching as well. A low space algorithm cannot write down an entire matching on its cut tape, on its work tape, excuse me. So there's a standard solution for low space algorithms, which is that you just ask the oracle or the subroutine for one bit of the cut when you need it, right? So for example, for each edge, you ask the oracle, is this edge part of the minimum cut? Now, if the oracle or subroutine is not pseudo-deterministic, then its answers may be inconsistent, right? So imagine here that Hobbes is a low space algorithm and Calvin is a randomized minimum cut oracle. Now Hobbes may ask Calvin, is this red edge part of the minimum cut? And Calvin thinks of this particular minimum cut and says yes. Now, later in the algorithm, Hobbes might want to recover some information about this edge. So he asks Calvin again, is this edge part of the minimum cut? Now Calvin, being randomized, thinks of a different minimum cut this time and says no, right? And now Hobbes gets two different answers for the same question and is confused. If Calvin was pseudo-deterministic, then both times he says yes or both times he says no, right? Good. Now let's move on to the third reason, which is privacy. And I mean privacy in a theoretical sense here. So the output of a pseudo-deterministic algorithm reveals less about its internal random bits. So imagine that Calvin is a randomized minimum cut algorithm and Team Rocket here is an adversary. So a randomized algorithm is essentially a matching, given, let's say we fix a graph as input, then a randomized algorithm is essentially a mapping from random bits to minimum cuts, let's say, right? So for example, Calvin thinks of some random bits and then outputs a minimum cut. Now Team Rocket can essentially see the minimum cut and guess what Calvin's random bits are, right? Because if Calvin now thinks of some different random bits, then he's going to output a different minimum cut, right? So the cut that Calvin outputs reveals a lot about his random bits. If Calvin was instead pseudo-deterministic, then it doesn't matter what random bits he's thinking of, he always outputs the same minimum cut, right? And so Team Rocket can't figure out anything from his answers. Good. So now let me tell you what's known about the global minimum cut problem. And I'm going to tell you about global minimum cut in 4 models: the sequential model, the parallel random access model, the streaming model, and the cut query model. And in 3 settings, so randomized, deterministic, and pseudo-deterministic. So first, in the randomized setting, essentially all 4 models have nearly optimal solutions. So in the sequential setting, there's an m log square n time algorithm. In the PRAM setting, there's an O tilde m work, O tilde 1 depth algorithm. In the streaming setting, there's an O tilde n space and O tilde 1 passes algorithm. And in the cut query setting, there's an O tilde n queries algorithm. For more details about where these results are, you can check our paper. In the deterministic setting, the sequential model has a nearly optimal algorithm. However, I would note that the log factors are quite large and it's not really practical. The parallel setting has a very, very inefficient algorithm, right? So very large polynomial work with polylog depth. In the streaming and cut query setting, nothing deterministic is known. In the pseudo-deterministic setting, in our paper, we essentially match the randomized bounds up to log and log n factors in all models. Okay. Now let me tell you the rough idea of our algorithm. So let G be a weighted undirected graph. And for the rest of the talk, I'm going to assume that the weights are actually positive reals, just for the sake of simplicity. So consider the following 2 operations. The first operation is that we add an edge with weight 0. And the second operation is that we pick an edge and we increase its weight very slightly, okay, with a very, very small epsilon. Now let G prime be the graph after applying either of these operations. The main idea is that any minimum cut of G prime or cut set of G prime is also a minimum cut set of G, right? The idea being that if you have some cut which is not a minimum cut, then we're not really changing edge weights so much such that it can now become a minimum cut, right? And also, if you add an edge with weight 0, then it literally doesn't change the weight of any cut, okay? However, the set of minimum cuts can become smaller, right? So let's say you have 2 minimum cuts and we ever so slightly increase the weight of 1. Well, then there's only 1 minimum cut left, right? So that's the idea. We're going to apply these operations repeatedly to finally obtain a graph G prime which has a unique minimum cut. Then we can run any randomized minimum cut algorithm on G prime, and we're guaranteed that it's also a minimum cut of G. So let me tell you how to do that for minimum ST cut first, just as a warm-up. So here's a simple fact that we'll use. If S and S prime are minimum ST cut sets, then so is their union. Okay, this is a fact about submodular functions in general. Thus, there exists a unique minimum ST cut set S star in G whose size is maximum, right? The idea being that we take the union over all the minimum ST cut sets. Now, our strategy is going to be that we perform operations on G such that the only remaining minimum ST cut is S star. Let me tell you how to do that now. We add zero weight edges of a star graph with S as the center, right? So this is applying operation 1 and minus 1 times. We just add a zero weight star to the graph. Now, we give each edge in the star a really small weight epsilon. So this is applying operation 2 and minus 1 times. Good. Now, for any ST cut set S, this is the weight of the cut, right? We have the cyan part, which is the weight of the cut in the original graph. And then we have this other part, which is essentially the weight of the new edges, right? The edges from the star graph. And just note that the first part is minimized when S is a minimum cut of G. And the second part is minimized when the size of S is maximum. And because epsilon is so small, the first term dominates the second term, right? So if you put both of these constraints together, keeping in mind that the first term dominates the second term, then this whole equation is minimized when S is a minimum cut of G with maximum size, right? And as we said, this is uniquely S star. Thus, the minimum ST cut is now unique, and we can run any randomized minimum ST cut algorithm. Okay, now let's talk about global minimum cut. So first, observe that the minimum ST cut construction did not depend on T, right? It only depended on S. So we select an arbitrary S and perform the previous construction. Now, let T be the set of all vertices T such that the minimum ST cut is also a global minimum cut, right? So what we essentially do is take all of the minimum cuts and add all the vertices that appear on the opposite side of S. So let these vertices be T1 to Tk in order. Note that for any T in the graph, the minimum ST cut is now unique, right? So in particular, the minimum, let's say STK cut is now unique. Thus, our strategy is going to be to apply operations such that the only remaining minimum cut is the cut which separates S and Tk. So let this cut be S star, okay? Let me tell you how we're going to isolate it. So in the last step for ST minimum cut, what we did was add a very low weight star to the graph, right? So we're going to try to do the same thing, but instead of adding the entire star, we're going to add a partial star to the graph, okay? So we pick the first B edges of the star, and we only add those with an even smaller weight delta, okay? So a much, much smaller weight delta. Now, B is just a parameter, right? But here's a fact. With access to a minimum cut algorithm, we have a way of testing if B is either larger than Tk or if it's smaller than T of k minus 1. Okay? This is a fact we show in the paper. Now, this means that just by applying a simple binary search, we can obtain B in this range from Tk minus 1 to Tk, right? So let's just assume now that B lies in this range. Good. Now, just note that the weight of every minimum cut S of G increases by delta per vertex, right? A delta per vertex on the opposite side of S, I should say, right? So, for example, in this minimum cut shown in the picture, you can see that there are three vertices on the opposite side of S, right? The red vertex, the blue vertex, and the green vertex. And um, the weight of all three of these edges increases by delta, right? All three edges in this new star, partial star, increases by delta, right? So the weight of the whole cut increases by delta per vertex. And this is true for all minimum cuts S except S star, right? Because S star is the cut where one of the vertices on the other side is TK. And TK is the only vertex on the opposite side of S in any minimum cut which didn't receive this extra delta weight, right? So S star is the only cut which didn't receive delta per vertex. Thus, S star is the sole remaining minimum cut. And the minimum cut is now unique, so we can run any randomized algorithm. Good. So in summary, for ST minimum cut, we just add a low weight star graph rooted at S to the graph, and then run any randomized algorithm. For global minimum cut, in addition, we add a second very low weight partial star graph rooted at S, and then run any randomized algorithm for global minimum cut. So the algorithms are all really simple and really efficient. So that's it for today. Thank you.